Okay. My name is Yonghong Yan. I'm from the University of South Carolina. So this is a work done by two of my students, Philip and Yudong. They have been playing with OpenMP, and when we starting taking the course learning OpenMP, and they are thinking maybe some realization of how parallel execution, how fork join is realized, and so it helped them to understand how the parallel execution is happening. So we're using the OMPT tool interface is for building first-party tool. What they do is, you put a callback, and so you don't need to instrument your code. So the whole interface is providing to a developer, so they don't need to instrument the code. They don't need to change the runtime. As long as you have the callback implement function of tracing or analysis, then you don't need to change the code. You don't need to change the runtime. And you just write your code, first-party code. And the details of the OMPT interface can be found from the spec, and there are, I think close to 100 or even more than pages document specify different kind of event and a different interface. Okay, there are a lot of events. I'll show some of them. Parallel begin, parallel end, thread begin, thread end, task create, implicit task, and or target event, task dependency, and synchronization event. Those are the events that when it happens, it will call certain callback. So basically, from the tool developer, as long as you specify the information, what you want your tool to do when the event are triggered. Okay, so what we have been doing is using this example, very simple example. So this example, the AXPY, we make a little bit of changing on AXPY just to make it fun to see how the event are being generated. So in that code, it has two parallel two function that contains OpenMP directive. So one, the parallel for basically initialize the simple array. Another one is the parallel for, is the parallel region, then a parallel for, then after that we have barrier, then the master. And that's the two functions, and we call the first that function twice, and then we call this function once. So that's how the code will be executed. Pretty simple, right? But it's not just the AXPY. We add these two things just to make it fun. Okay. Now after we ran the code, we use OMPT, so we don't need to change this code at all. We don't need to do instrumentation or recompilation. And we are able to generate a graph. This is a pretty rudimentary graph of a different color. We're trying to make it as beautiful as possible, but it's not showing the whole detail, but it's showing the most important information. So I'm going to go through each part of that. For example, we call the first init the twice of these two init function, and because it has a parallel region, and the parallel region will basically include a parallel begin event, which will be triggered by the master thread. Am I entering this? Yeah, good. So we're triggered by master thread. This is the master thread, the parallel begin, and then after that, and or the worker thread, including the master thread, will have a implicit task begin. So that implicit task begin will be indicated that each thread will start executing their own portion of that parallel region. Okay, and then they will enter into callback work, which means that they are starting to enter into the work sharing region. That work sharing region basically is a static scheduling, so each thread will do the work. And after that, it's a barrier, the implicit barrier, the join barrier. At that point in time, that's indicated by the red color. There are 4 events happening for that barrier. Okay, the parallel sync begin, sync wait begin, sync wait end, and sync end. So it's a sequence of 4 events happening, because thread may enter into wait state, synchronization state, then enter into wait state. So that's what happened by each of these 4 threads. And after they finish their execution, they will enter into end state, which means indicate we indicated that parallel region is complete by each specific thread. Okay, and then after that, all the thread will join into parallel end event, which is only triggered by the master thread. Okay, so that for the first call of that init function. And after each thread, since we call these two functions in consecutive way, so the master thread will immediately enter into this another parallel begin that indicate a second call to the init, but all other thread will enter into idle state because after their synchronization they don't have work to do. So other non-master thread, they will be idle waiting to be summoned, right? So that's in this the execution start for the second parallel region. That's what happened at the same way as the first init call. Make sense? So that's how we realize this event happening. Now for that call, that's a little bit more complicated. There's the parallel region, there's the fall, there's the barrier, and there's the master directive. So, but actually the same thing. Each directive is associated with different set of event. So as long as we trigger this event will be triggered by the runtime, and we have a callback to handle this event, we are able to collect information, or that's tracing this information, and we're live in this one. So the same thing here, and the parallel begin, implicit begin. Then there's the work. The work indicates that work sharing part. So that's the green part for work. Okay. After that, because that for loop include a implicit barrier, right? So that's why there are 1, 2, 3, 4. Now 4 of these red box. It's required. It's basically 4 events that required for a single barrier synchronization. That's why there's the 1, 2, 3, 4. It's sync begin, wait end, wait begin, then wait end, and sync end. So it's 2 pair of begin end event. So that 4, 1, 2, 3, 4 is for the barrier of that implicit work sharing loop. Now there's the explicit barrier right after this one. It's not necessary, but it's just to demo how we can get this information. That's another 4, 1, 2, 3, 4. Then another 1, 2, 3, 4. Another 4 red box for the event associated with that explicit barrier. Okay, so now after that, because this barrier will be it will synchronize all the threads, so every thread will have that 4 event. After that, then there's the master directive, which means only the master thread will execute the code, right? That's what happened here. The master, there's 2 events called master begin, master end, indicate that master thread will trigger these 2 events and execute this printf call. But all others, they don't have anything to do at this point, but they will directly enter into the join barrier of the top level parallel region, right? Master don't have barrier. Master have no implicit barrier. The single has an implicit. If you have a single, we're different. But in this case, the master. And so only master that execute this master region, and after that, they all enter into that implicit barrier or with the join barrier. So that's basically typically indicate the end of that parallel region, which will be the which will show as the implicit end by each of the thread. Yeah, that's basically indicated the completion of that call. And go the last event is this callback thread end, which basically the execution finish. So all the thread will terminate, and this one is also means the thread will be terminated. Okay, so that's how we realize the way we do that. How we do this tracing. So internally, and each thread has its own tracing buffer to store all the event consecutively, and also the information associated with each event. So when an event happens, it will add to a big array of this tracing information. Now we have a new term called the lexicon or lexicon. I call it lexicon. It's the lexical code region of the OpenMP. So if you have OpenMP directive, each means it indicate a lexical region of that code. And in the callback, you can find that information, which is the binary address, by that code pointer underscore RA parameter of most callback call. So each time a callback is triggered, it will passing that binary address, which will associate with the code region of that using the OpenMP directive. So that's the information we can capture. And each thread has its own lexicon stack. because you may have a in that example we have that multiple Lexington it's nested, right? It's not nested parallel, but it's nested Lexington region. So that's why each thread has a stack of that Lexington region object stored internally, and each Lexington has a linked list connecting all the event happening for that Lexington. Because the same code region may be called multiple times. If you have a while loop, while loop, then internal you have a same function called again and again. The same region may be called multiple times. That's why there's a linked list for those events that are associated with a particular Lexington. For parallel region, which is a special case, and we store that implicit task region in the master thread parallel region object. So that's the reason why we can connect this link here, because now creating this link is pretty straightforward. Just each thread have their consecutive event list, right? But creating this link is required that the master thread store the implicit task region information. And we also, in tracing all this event, we also add some performance profiling features, like they can collect a timestamp, they can read a PIP counter, and can read the power using a REPL. So they can collect anytime the event which we trigger, but as long as you add whatever information you want to collect, you can do that. And after that, the GraphML output is just dump the tracing date into a GraphML file. That GraphML file will be realized like this. Okay. Make sense? Any question? Okay. Yeah, the color indicate, the green we using color indicates a thread is doing some real work. And the red indicates the thread is doing synchronization. So mostly. And something close to green, like this one, is doing some work but not a work sharing. Like master is doing some work, it's useful work, but it's a different kind of work. It's work sharing. And the yellow is indicate a thread is idle, do nothing but waiting for work to do. So the color would basically indicate the more green the better, because we want most thread to do the work. But this color is just the same size. The ball is just indicated that kind of event. It does not indicate how long a thread executing each one. It's just a point of that event. Okay. That's what has been done. The whole realization is pretty straightforward, since we just need to dump the tracing date into GraphML file. Then we realize, and we have a tool that can do graph layout, so we can generate this hierarchical layout graph. And the most complicated part is internally how we store this tracing date. And tracing data could be huge if the loop is big, if it or a large number of iteration, and also how we store, how we internally store this information that is related to a single Lexington. Okay. 2 p.m. Okay. That's it. I'm off. I'm done. Thank you.